Thanks, everyone. So we're going to talk about category theory. Why do we care about category theory? Well, I assume we all like Haskell. And one of the reasons I like Haskell, as opposed to something like Lisp, is because it has types, and also it has type classes. So once we understand what is the structure of something like a functor or a monad, then we can just recognize that, and without spending a lot of cognitive energy, we can do fmap or bind. And category theory does something similar for the whole of math. So we can take different kinds of mathematical objects and package them into categories, and then we can shift the focus away from what are the particular properties of each mathematical object and shift the attention more into what they have in common. And similar to how it works in type classes, we can start seeing repeated patterns of structure. So we're going to talk about categories. But before that, we're going to talk about pre-orders, which is a simpler kind of category. And before that, we're going to do a quick review of sets, because we're going to be using sets. So we're going to go through that quite quickly. So a set, as far as we care about it, is a bag of dots. So here's a way we can represent it. And this symbol means A is an element of A. We can have a set of natural numbers. We can have a set of Booleans. There is also an empty set that doesn't have any elements. And given two sets, A and B, we can define the product of A and B as a grid of dots, where there is a dot for every pair of A and B. A is a subset of B if every element of A is also an element of B. And we can define for example, 1, 2, 3 is a subset of the natural numbers, while 1, 2, 3.6 is not. The empty set is a subset of every other set, and every set is a subset of itself. And now we can define relations. We can think of them like relationships. So relation on A and B is a subset of the product. So we can think of these pink elements as being related. So 1 is related to 1 and 2 is related to 1. Now a function is also a relation with two extra properties. So one, if a function is from A to B, is that every A is mapped to something in B. And the second property is that every A is mapped to a single B. So this is what a relation looks like if it is a function. It's like the third example is a function. The first two examples break the properties. And a function is called injective if no two things go to the same place. And it is called surjective if every B is mapped by something in A. And it's called bijective if it is both injective and surjective. And this is also known as a one-to-one correspondence. Now we can define composition. So if you have two functions, and the codomain of one is the domain of the other, we can obtain a new function by first applying f and then g. And what if we have three functions that are composable? There are two different ways to compose them. We can first apply f, and then the composition of h and g, which is the pink path. Or we can apply g composed with f and follow it with h, which is the blue path. And we can say that this diagram commutes, which means that there are two ways to go from A to D, and they're the same. So this equation is true. So we can drop the parentheses and just say H circle G circle F, because it doesn't make a difference. So a partition is a surjective function. So in case you forgot, surjective means every B is mapped by some A. So we can see this as a way to say we have 4 people and they belong to 3 teams. And the first 2 people are in the same team, and the other people are in different teams. So once we have a function like that, we can lose the dotted lines, and we still have all the information of which people are in the same teams. Now, if we have a set A, and we have 2 different partitions, so we have 2 different surjective functions, is there a way to define an order between them? And we can say that P1 is less than or equal to P2 if there exists a function h that makes this diagram commute. So in this example, every blob of P1 gets assigned to some other blob in P2. And if we had a set of 3 elements, what we can do is we can write out all the possible partitions that exist, and then we can think which ones are less than which. So we can draw an arrow between them if one is less than the other. And this is called a Hasse diagram. And in this example of partitions, if it's more refined, it's smaller than if it is more blob, which is bigger. And also you can notice that not everything is comparable. So for this middle row, there is no comparison because we cannot define such a function that makes the other diagram commute. So once we know what is the order, we can define the join operation. So what is the join of these 2 partitions? Well, to answer this question, we're going to have to look at the Hasse diagram, because the answer is the least partition that is bigger than both. So both of those are in the middle row, so the join of these 2 partitions is the one at the top. And the meet of 2 partitions is the greatest partition that is smaller than both. So we're going to define preorder now. So a preorder is a set S that also has a relation from S to S. And we name this relation with this less than or equal symbol. And also it has 2 properties. One, for every S in S, S is less than or equal to S, which is called reflective. And 2, if S1 is less than or equal to S2, and S2 is less than or equal to S3, then S1 is less than or equal to S3, which is called transitive property. So what are some examples of preorders? Well, partitions that we just saw is a preorder because it satisfies these properties. And the order relation is as we defined it with the function. We can also define the Booleans to be a preorder by setting false to be less than or equal to true. So this is the Hasse diagram for bools. And we can see that meet is and join is or. Another example is the power set preorder. So a power set is the set of all subsets of a set. So if we write all the subsets out, so here we have the subsets of 1, 2, 3, we can define the less than or equal relation to be the subset relation. And in this preorder, meet is intersection and join is union. And another example we're familiar with is the natural numbers with the usual ordering. And meet is min and join is max. So we're going to define upper sets. And so if P is a preorder and U is a subset of P, U is an upper set if it satisfies that if P is an element, then so is anything bigger. So this is what it might look like. This is the example from the power set preorder. So the pink elements form an upper set because for each one of them, all the bigger ones are also part of the set. And as a counterexample, this is not because it has missed a couple of elements. And there's the dual concept of lower set, which is the opposite, which means if P is an element, so is anything smaller. And why we mention upper sets is because if we get all the possible upper sets of a preorder, these themselves form a preorder. So this is the example from Booleans. These are all the possible upper sets. And the less than or equal relation here is the subset relation. And one of the important functions between preorders are called monotone maps. And these are functions that preserve the order. So a monotone map is a function such that if x is less than or equal to y, then f of x is less than or equal to f of y. This is a simple example of a monotone map, which we have the natural numbers and a function that multiplies by 2. So this preserves the order. Another example of monotone map, we have the preorder of power set, and we define a function that returns how many elements are in every set. And this also preserves the order. So on the right side, we have the natural numbers. OK, so we're going to define category. So a category consists of 4 pieces of data, and it satisfies 2 rules. So the data, 1, there is a collection of objects. 2, for every 2 objects, C1 and C2, there is a set of morphisms from C1 to C2. Morphism and arrow are interchangeable. It means the same thing. So for every 2 objects, there's a set of morphisms from C1 to C2. It's a set, so it could be empty if there's no arrows. It could be 1 arrow. It could be 10 arrows. And in terms of notation, we can say F if it goes from C1 to C2. C1 is called the domain of the morphism, and C2 is called the codomain. OK, the third piece of data is that for every object, there is an identity morphism from C to C, and it's called the identity on C. And the fourth piece of data is that if we have any 2 composable morphisms, there must exist the composite morphism in the category. And the 2 rules are that the identity morphisms are the unit for composition, both the left and the right unit. So if you compose anything with identity, it doesn't change the result. And the second rule is that composition is associative, as we saw in the previous slide. So you can compose things in any order. So what are some examples of categories? Well, every preorder is a category. So from every preorder, you can get a category by doing the following. The elements of the preorder become the objects of the category. And what about the morphisms? Well, if A is less than or equal to B, then there is 1 morphism from A to B. Otherwise, there is no morphism from A to B. And the fact that the less than or equal relation is reflective means that every object has an identity morphism. And the fact that it is transitive means that all the composites exist. And also, you can go the other way. So if we have a preorder and we look at the Hasse diagram, this kind of looks like the diagram, like the drawing of a category. But there is one caveat. If there are 2 parallel paths from A to B, we must declare them to be equal. Because a category could have 10 morphisms from A to B, but in terms of the preorder, either A is less than or equal to B, or it isn't, but there is no concept of having multiple different ways for A to be less than or equal to B. So if we say B after A equals D after C, then we got a preorder from the category. OK, now we're going to look at some kind of basic examples of categories. So this category has only 1 object and only the identity morphism on that object. And it has a name. It's called 1. You might think that's not very useful, but here's another category that doesn't have anything. No objects, no arrows. It's kind of like the equivalent of the empty set for categories. Then we have a category with 2 objects and 1 morphism between them called 2. A category with 3 objects, 2 morphisms and the composition called 3. And in general, we're going to stop drawing the identity morphisms. And also, we're going to stop drawing the compositions as well, because by definition, they have to exist. Otherwise, this thing wouldn't be a category. A category is called discrete if it has no other morphisms other than the composition. So this is kind of like a set that just has an identity on every element. And an important category that comes up a lot is called set, and it is the category of all sets and functions. So in this category, the objects are all the sets. Morphisms are functions between sets. Identity is a function that just returns its argument. And composition is the normal function composition. some more examples of categories. We can define the natural numbers as a category. So if we have a category that has one object, we can call it Z, and there is a morphism S. And also, we haven't drawn it here, but there's also an identity morphism on Z. So there's not a lot we can do here, but we can go around the object with S. And because there's only one object, yes?
What would be the difference between ID and S in this case?
Yeah. So ID doesn't do, so ID is the unit for composition. So if you compose it with anything, it doesn't do anything. The S is some morphism. We haven't said what it is, but we assume it does something. So every time you compose with it, you get something different. So yeah, if this was ID, that would be the category 1 from the previous example. But yeah, this one is not. It has an ID arrow and some other morphism. And because there is only one object, S is composable with itself because it goes from Z to Z. So there's not a lot we can do, but we can go around the object 1 time, 2 times, 3 times, and we can keep going. And every path of length n corresponds to a natural number n. Okay, what about this example? If we had friends and we had a morphism from A to B, if A was a friend of B, is this a category? Well, we can assume identities exist, but it's not a category because Jane might not even know who is Joe. What about something like a tube map where the objects are tube stations and you can go from A to B, and then there is a morphism from A to B if you can go from A to B via the tube? Yeah, this one would be a category because it would have as identity stay where you are, and it has composition as well. And both of these 2 previous examples were graphs, and more generally for any graph, you can define a category, which is called the free category on that graph, by setting the objects to be the vertices and setting a morphism from A to B to be all the paths that you can go from A to B. So this is why our friendship example didn't work, because we set the morphism to be a direct friendship instead of a path. So what is an isomorphism? So in a category, if there is a morphism F from A to B, it is called an isomorphism if there exists a morphism G from B to A such that G after F is the identity on A, and F after G is the identity on B. So an example, in the category of set, the isomorphisms are precisely the bijective functions. So a bijective function can be thought of as just a relabeling of the elements. And if a function is bijective, you can always define an inverse. So we start to see that generally there seems to be 2 different ways to define things. One is to look inside a set and look at what elements it has. And the other way is to look outside of the set, don't care about the elements, but look at the morphisms it has to other sets. So to give an example from real life, let's say you're at a party and you've met someone and want to know them better. There are 2 ways to go about that. One is to say, hi, tell me about your inner thoughts and feelings, your fears, dreams, and also how do you score on these 5 personality traits. The other way is to say, oh, hi, actually, I don't care about you, but tell me about your friends. Who are they? What about your employer? Where do you work? Where did you work before? Where did you go to university? Are you a member of any other organizations? Who do you follow on Twitter? So one way is trying to go inside a person's psyche, and the other way is trying to understand them in the context of their relationships to other people. And we've seen a similar example here, because we defined bijective function in 2 different ways. One is to look inside the set and check okay, is every element mapped to a unique element on the right, and vice versa. And the other way was to say, f is bijective if there exists another function g such that their composition is the identity on both sides. And category theory generally does the second way. And this has the benefit that we don't have to know every single thing about the... So to do the first way, you have to know what is set, or what is every particular thing you're studying. The second way works for every category, the definition of isomorphism. So continuing on this vein of defining objects based on their morphisms to other objects, let's think about the empty set. What makes it special? Well, you could say it is the set that doesn't have any elements, but this is doing it the first way, by looking inside the set. How can we do it without looking inside the set, but instead looking at the functions it has to or from other sets? So are there any functions from the empty set to other sets? Well, if we remember the definition of a function, it was the subset of a product. The product of the empty set with some other set is the empty set. And the empty set only has one subset, which is also the empty set. So yes, there is a function. It's the empty function, which does not really map anything to anything. But there exists a function from the empty set to every other set. And this is how we can define the empty set by looking at the functions, by saying it's the set that has a unique function to every set. And more generally, an object is called the initial if for every object in the category there exists a unique morphism from that object to every object. So the empty set is the initial object in the category of sets and functions. And also, any two initial objects are isomorphic. And we can quickly think why this is true, because if I1 is initial, it has a unique... So let's say we have two initial objects, I1 and I2. Because I1 is initial, there is a unique morphism to I2. Because I2 is initial, there is a unique morphism to I1. Let's call these F and G. So I1 also must have an identity morphism. So now suddenly there are two morphisms from I1 to I1, the ID and also G after F. So these two must be the same. And the same on the other side. So what we've written is the definition of isomorphism from the previous slide. And also there is something called the terminal object, which is the opposite, which is an object that has a unique morphism to it from every object in the category. So in the category of sets, the terminal object is any object that only has one element, because there is only one possible way to define a function to a set with one element, and that is to map everything to that element. And this brings us to the concept of duality. So if we have any category C, we can define the opposite category of C by turning all the arrows around. And if two morphisms are composable in C, they're also composable in the opposite category, but it's the opposite order. So in one case, we get G after F, and in the opposite category, we get F after G. And there is something called the duality principle, which says for every true statement, you can get another true statement by swapping domain with codomain, and H equals G after F with H equals F after G. So basically, swapping all the arrows and reversing the composition direction. So if we said any two initial objects are isomorphic, we can say any two terminal objects are isomorphic and have it proven for free if we proved it for the other case. So categories are mathematical objects of themselves. So there is a category whose objects are categories. But what are the morphisms between categories? Well, they are functors. So a functor is a transformation of one category to another category. And it needs to preserve the structure of the category. And by structure, we mean the identities and the composition. So this is the definition. a functor f from C to D consists of two pieces of data. One, every object C in C is mapped to an object f of C in D. And two, every morphism from C1 to C2 in C is mapped to a morphism f of f from f of C1 to f of C2. And the two rules are that the identities and the composition are preserved. So every identity arrow has to stay together with the object after it's mapped. And you can compose on either side and take the functor, and you have the same result. So let's look at what functors look like, kind of in general. So if these are two categories, these blue arrows could define a functor if we map the objects to the right side and the morphism on the left to the morphism on the right. This one can also be a functor. It maps both objects to the same object, and the morphism is mapped to the identity of that object. This one could also be a functor. It maps the morphism to the composite on the right. This one is not a functor because there is not even a mapping for the morphism on the left. This one is not a functor because it has mapped the morphism in the wrong direction. Well, it turns out this is a contravariant functor, which is the same as a normal functor, also called covariant, from the opposite category to the other category. And some more examples of functors. So for preorders, functors are monotone maps. So this example of multiplying by 2 on the natural numbers is a functor between the preorders. Here's another preorder where there is an arrow from A to B if A divides B. So here we have all the factors of 30, and we can define a functor to the power set preorder by sending every number to the set of its prime factors. And next, we're going to talk about natural transformations. Sorry, one sec. So hopefully we understand what is a functor from C to D now. But what if there were two functors from C to D? We had F and we had G. Wouldn't it be nice if you could travel from F to G? So let's have two categories. It's one on the left and one on the right. And we have defined two functors. F sends you to the left ear, and G sends you to the right ear. Imagine you are object C, and you take the F functor, and you end up on the left ear. And then you think, oh no, that was a mistake. I meant to take the G functor. What am I going to do? So a natural transformation is going to give you a morphism for every object in C that takes you from where you are to where you would have been if you had taken the G functor. So here's the definition. If C and D are categories and F of G are functors, a natural transformation consists of the data is a bunch of morphisms. So it's all these green arrows that take you from F of C to G of C. So for every object in the category C, you get one green arrow. And the rule is called naturality condition, which says that if you take F of F, which is the pink arrow on the left ear, and then take AD, which is the D component of A, this is exactly the same as taking AC, which is the green arrow over the ears, and G of F, which is the blue arrow on the right ear. Okay, sorry. What about this example? Is this a natural transformation? Well, it's not, because there's no arrows that connect F of C and G of C, or F of D and G of D, and you can't just add arrows where they don't exist to make it happen. And some other examples, in the natural numbers, if you have two functors, one multiplies by 2 and the other multiplies by 3, we have all the green arrows from 2x to 3x as a natural transformation. And an example from Haskell, if we imagine a category whose objects are Haskell types and whose morphisms are functions, and that's the same category on the left and right, we can have two functors. One takes a type A and gives you maybe A. The other takes a type A and gives you list of A. And a natural transformation between them would be a function like maybe to list that converts a maybe A to a list of A. So we are near the end now. And I wanted to ask you to look at this picture again. So this was the upper set on a preorder. In this example, we have the power set preorder, where the less than or equal relation is the subset relation. So the upper set of 1 is the upper set that contains 1 and anything bigger than it. The upper set of the set 1, 2 is the blue elements, is 1, 2, and anything bigger than it. And we can see that 1 is a subset of 1, 2, and also that the upper set of 1, 2 is a subset of the upper set of 1. That's not very hard to prove. We're not going to prove it now. But what's interesting about it is that it's a two-way relation. So it's an if and non-leaf condition. And this happens to be something called the Yoneda embedding on the category of preorders. On preorders. So we don't have time to look at the Yoneda lemma in detail, but I just wanted to give you a little taste of it. So it has been called one of the most important results in category theory. And it's not only a useful tool, but it's a bit of an interesting philosophical idea. So what it says is that you can completely determine an object based on the network of relationships it has to other objects in the category. So an example from particle physics would be if you have some particle and you don't know anything about it, but you shoot every other particle to it and you see how it reacts, that's the same as knowing everything there is about the particle. So we saw what it looks like in preorders, and I want to show you a bit of the Yoneda embedding in the more general case. So imagine we have a category, C, it could be any category. Can we define a functor from C to set? Well, if you recall the definition of category, we said between every two objects, there is a set of morphisms from A to B. So we can do a trick, which is to fix an element A, and then define a functor in the following way. Every object X is mapped to the set of morphisms from X to A. So here, X would be F1, B has two morphisms from A to A, so it's F2 and F3, and A just has the identity. So that's how we map objects. A functor also needs to map the morphisms. So how can we do that? Let's take F. It goes from X to B. This one is a contravariant functor. Yeah, I forgot to say, we can define two functors from C to set. By choosing, for any object X, we can send it to the morphisms from X to A, or to the morphisms from A to X. So we get two functors. One is covariant, and the other is contravariant. This one is the contravariant one. So F goes from X to B, so we need to send something from F to F3 to F1. Well, what's F2? F2 is a morphism from B to A. And how can we transform this to a morphism from X to A using F? The only thing we can do is pre-compose it with F. So this notation with the dash is like a lambda function that replaces dash with the argument. So we compose with F in the beginning. Okay, so we started by fixing A, and we got a functor to set. If we fixed B, we get a different functor to set. And we call these representable functors. These are the contravariant representable functors. And also we call them 8 subscript A and 8 subscript B. Cool, so we have a mapping from every object in C to set. Now the next question we might ask, is this mapping itself a functor? And we can't prove it now, but it is. And this functor, what is the type of this functor? Well, it takes things in C, so it goes from C to the category whose objects are functors from C up to set. So this functor is called the Oneida embedding. This weird notation with the brackets, we haven't mentioned it, but it is the category whose objects are the functors from C up to set. And the other interesting thing is that this functor is not just any functor, but it is full and faithful, which means that the way it maps morphisms, it's bijective. So you can go both ways, similar to the statement we saw for preorders. So what this says is that the set of morphisms from B to A is isomorphic to the natural transformations from HB to HA. So we can choose which slide we want to work on. Do we want to work on the objects in C, or do we want to work with the morphisms they have to everything else? So if you remember our example of meeting someone at a party by asking about their friends, this is kind of like doing this in the opposite direction. And to be precise, you can't just ask about some friends, you have to ask about all the friends. Because what if they leave out an important friendship that would change your opinion? And this gives us a dual way. So we have a third way of meeting someone at a party, which is to not talk to them and instead talk to everybody else in the world and ask them what they know about this person and what is the relationship. So you do have to ask everyone in the world, because if you just ask people at the party, for example, if they are colleagues, they might know the work persona of the person. So it's not the whole picture. Then if you add more people, if you ask parents, teachers, ex-partners, bus drivers, baristas, you build up a more full picture. And when you asked everyone, you know everything there is to know. So your job's done. Yeah, that's my overview of category theory. We looked at preorders, categories, functors, natural transformations, and more generally the concept of defining things based on the morphisms they have to other things instead of studying them directly. These are some resources I used for this talk. And any questions? Yeah.
Thank you very much, Irene. Thank you again, Irene. Does anyone have any questions? Okay.
Thank you for the talk. I have a very low-level question. So the definitions of preorders and categories seem maybe superficially very, very similar.
Sorry, can you repeat?
Definitions of preorders and categories, superficially they seem very similar. Mm-hmm. Is there anything deeper going on? Why they are so similar?
Okay, so a preorder is the same as a category that only has maximum one morphism from between two objects. So category is more general. You can have as many morphisms as you want. So a preorder is a bit smaller thing, but they are similar, yeah.
That's the only difference, like the number of morphisms.
Yeah.
Yeah, so you showed us how category theory relates with concepts in Haskell, like functors and natural transformations. I was wondering if there is some way to explain in category theory simpler concepts like monoids or semigroups or maybe applicatives.
Yeah, generally there is. Actually, for monoids, the example we showed of the natural numbers was a monoid, but I didn't mention it because it can get a bit confusing. So a monoid is a category with one object. And I think most of those things would have a category theoretical concept, but I don't know all of them. Yeah.
Any more questions? Okay, fantastic. Thank you again, Irene. That was fun.
Thank you.